Hello. In this video, we're going to look at trig limits. Now, before we begin, we need to remember a few trig identities that are important for working with trig limits. And of course, you should memorize these identities because you're not going to have a formula sheet on any tests or exams. So the first identity that you should know is that tan of theta is equal to sine theta over cos theta. Again, this is less of an identity and really more of a definition. Tan is sine over cos. You should know that one. And you should know the three reciprocal identities. So sine theta is the same as 1 over cosecant, or you could think of cosecant as 1 over sine. Cos theta is 1 over secant theta, or again, secant is 1 over cosine. And tan theta is 1 over cotan theta, or another way of thinking about it is cotan is 1 over tan. Now the next three identities are kind of fun. We know that sine squared theta plus cos squared theta is 1. Hopefully you remember this from the unit circle. So you draw a little triangle in the unit circle. You know the x portion is cos theta, the y portion is sine theta, and the hypotenuse is 1. So when you use Pythagoras, you get cos squared and sine squared, giving you 1 squared, which is just 1. Now that's the fundamental identity, and you can derive two more identities from the first one simply by dividing. So let's say we wanted to find this one with a tan. What I do is I take the original identity and I divide the whole thing by cos squared. I'll show you how it works. So we start with sine squared theta plus cos squared theta equals 1. Because we remember that one, and then we say, well, what if we divided everything by cos squared? So cos squared theta, cos squared theta, cos squared theta. Well, sine squared theta over cos squared theta will be tan squared theta. Cos squared theta over cos squared theta will be 1, and 1 over cos squared theta will be secant squared theta. And there you go. You've just derived your second identity. For the third one, you could try this on your own. You divide by sine squared theta, and you'll get 1 plus cotan squared theta equals cosecant squared theta. Now, a couple more identities that are important to know about. Sine of a plus b is equal to sine a cos b plus cos a sine b, and then sine of a minus b is the same thing but with a subtraction. Cos of a plus b is cos a cos b minus sine a sine b, and when you've got the negative in here, it changes to a positive over there. One last one, you can take this sine a plus b and turn it into sine a plus a. So if I was to have sine a plus a, that would give me sine a cos a plus cos a sine a, which if you look at it, you have a sine a cos a and a sine a cos a, so you have 2 sine a cos a, which instead of using the letter a, we could use the letter theta, and that's this identity right here. Sine of 2 theta is 2 sine theta cos theta. So without looking at any identities, let's see if we can remember which of the following is not a trig identity. All right, so hopefully you gave this one a try. The correct answer is B. B is not an identity. Although it looks like C is not an identity, D is an identity, and what we've done for C is move the secant to one side and move the 1 to the other side to give us the negative 1. So C is actually technically correct. It is an identity. It's just a rearranged version, but B is not an identity. Now, which of the following is false? All right, hopefully you gave this a try. If you think about our unit circle, over here at this point, we have the coordinate 1, 0. 1, 0, which means that sine of 0 is 0, and cos of 0 is 1, which makes tan of 0 equal to 0 over 1, which is 0. So this is correct, this is correct, this is correct, but cotan of 0 is equal to 1 over 0, which is undefined. So this is the false one. C is false. So let's jump into our trig limits. This is part of 3.3 in your textbook. And the motivation for this section is to determine this limit, sine of x over x as x approaches 0. And again, just because calculators can sometimes lead you astray, they're still helpful to at least start with. And so we're going to try plugging in x equals 0.1 or 0.01. We're going to see what happens on our calculator. So go ahead and get your calculator out, set it to radians, and try plugging in sine of 0.1 over 0.1. All right, assuming you gave that a try, you should be getting 0.998. Now, if you plug in 0.01, you should get much closer to 1. You're going to get 0.99998, so I think 4 nines and then an 8. But when you plug in 0, you get undefined. When you plug in negative 0.1, you get 0.998. And when you plug in negative 0.01, again, you get those 4 nines and then an 8. So if you were to take a guess, as x is approaching 0, what does it appear these values are approaching? Well, to me anyways, it looks like they're approaching 1. So we think this equals 1. Maybe? Question mark. It appears that we have some evidence for it equaling 1, but we definitely don't have a proof. We don't have anything close to an algebraic explanation of why that is true. So we do need to do some more work, but we're gonna suspect that it's 1. Now, we could write this with a theta instead of an x. And in fact, this result is so important, it's going to be called a theorem. And so as theta approaches 0, sine theta over theta, which is the same as sine x over x, it is indeed equal to 1. That is true. Our guess is indeed correct, and it's actually a theorem. So we're going to prove this. This is going to be one of our first full proofs that we're going to look at. And to do so, we need a few pieces of information. Like the trig identities, we need one other piece of information before we get started. So we need to recall the area of a sector formula. Now, you may or may not have seen this in pre-cal, but I'll go ahead and give you the quick overview. A sector is this. So it's like a wedge from a circle, or you can think of it like a slice of pizza, and we need to find the area of this. Now the formula is 1/2 r squared theta, and if you're wondering where that formula comes from, well, this is going to be an r, because it's got length r, and this over here, the rounded part, if you remember from pre-cal, this is an arc length, so if this is theta and this is r, this is always equal to theta times r. Now, the way you find the area here is a bit hand wavy, but if you remember a triangle for the area is equal to 1/2 base times height. And well, this sector looks kind of like a triangle. So we've got a base of r and a height of theta r. So area is going to be 1/2 r times theta r, which is equal to 1/2 r squared theta. Now again, you might argue, well, Mr. Peters, this is not a triangle. Clearly this is like rounded on this side. And so yes, this is not a rigorous proof of this formula, and like I said before, we need to assume that something is true. We need to start somewhere. So we are going to start with this formula being true. Just to show you that it's true, if you think about a circle, the area of a circle is equal to pi r squared. And if I was to use this formula on a circle, well, in that case, theta would be equal to 2 pi. And so then I would get area equal to 1/2 r squared times 2 pi. The 2's would cancel, and you'll get pi r squared. So this formula lines up here with what you would expect the area of the circle to be. So maybe that gives you another piece of evidence. But again, you do have to take my word for it that the area of the sector formula is true. We have to assume some things in this course, so we're going to assume this is true without rigorous proof, and then we're going to use it to prove the important result. Now, this proof starts off with the following figure, and so we're going to diagram this and look at a quick Desmos animation before we get started on the actual proof, because we need this figure. So go ahead and give this a sketch. We've got a quarter circle, part of the unit circle on the XY axis, and then we've drawn a little triangle in here and a bigger triangle over here. All right, we're going to label some of these components. So since this is a unit circle, we're going to label the hypotenuse here 1. Now, inside, of course, we're going to have an angle theta. And we know that from the unit circle section from pre-cal, the x portion is going to be cos theta. And the y portion here is going to be sine theta. However, we probably didn't learn what this portion was equal to. Any ideas what this longer portion is? Think about it for a second. What might be the value of this? And you can't pick a specific value like 1 or 2. It's got to be some type of function. Well, we can actually use similar triangles to figure out what that side is. If you recall your similar triangles, we can draw this triangle here, this small one, sort of like this. 1 cos theta sine theta. And then over here, we can draw this bigger triangle right here. Maybe I'll draw it in blue here. And we know that this portion along here, the base of this triangle, is actually 1, because it's the whole length of the radius of the unit circle. So this is going to be length 1, and this over here is length question mark. Now the way similar triangles work is that the ratio of these two sides, sine over cos, has to be the ratio of these two sides, question mark over 1. So we get sine theta over cos theta has to equal question mark over 1. Well, question mark over 1 is just question mark, so that means that therefore our question mark is equal to tan theta, because sine theta over cos theta is tan theta. So there we go. We know that that side is tan theta. Again, if you've ever wanted to visualize what tan theta looks like on the unit circle, it's this extra portion outside of it, which is kind of cool. Now let's look at a Desmos animation of this triangle and these sides. So here we have the same drawing in the full unit circle, and what I want us to think about is what happens as the theta gets smaller. So here theta is getting smaller, and we can notice the triangles are shrinking, shrinking, and eventually the triangles are going to disappear when they just become a straight line. And so we have these triangles, this relationship here, and as it happens, I want us to notice something. There are actually 3 shapes going on. There's our smaller triangle, there's a slice, a wedge, a sector going on here. The green portion of the circle is the outline of the sector, and then there's the bigger triangle here. And I'm going to make a pretty radical claim about this, but I think you're going to believe me. We have 3 areas: the area of the small triangle, the area of the sector, and then the area of the big triangle. And I claim that the area of the smaller triangle is the smallest, the area of the sector is in between, and the area of the big triangle is the biggest. Hopefully you see that no matter what we have, whether this is a very big or very small angle, those 3 remain in that relationship. So returning back to our diagram, we could say that this section over here is number 1, this section over here is number 2, and this is number 3. And that the area of 1, 2, and 3 has that relationship, that 1 is the smallest area, 2 is the middle, and 3 is the largest. Well, let's go ahead and find those areas. So area 1. Well, area 1 is a triangle, And the area of a triangle is 1/2 base, which is cos, times height, which is sine. Area 2 is a sector, which is going to be 1/2 radius squared, which is 1 squared, times theta, which is just theta. We could simplify that to just theta over 2. And area 3 is going to be 1/2, base is 1, and height is tan theta, which again we could simplify to just tan theta over 2. And so we can make the following inequality. Because A1 is less than or equal to A2 is less than or equal to A3, we could write each one of these A1, A2, A3s in an inequality. So we'd have cos theta sine theta over 2 less than or equal to theta over 2 less than or equal to tan theta over 2. All right, well, let's go ahead and clear out that 2. So we're going to multiply by 2 to give us cos theta sine theta less than or equal to theta less than or equal to tan theta. Now, hopefully you should notice what I'm doing here. We have a string of inequalities. What we're trying to actually use is the squeeze theorem. So we want this inside portion to look like our target function, which is sine theta over theta. We're not quite there yet. And so what I'm going to do is I'm going to divide by sine theta. So divide by sine theta. Now tan theta, maybe I'm going to erase this for us. Tan theta we could write as sine theta over cos theta. So we could put sine theta over cos theta. So when we divide by sine theta, well, the sine theta on the left-hand side is going to disappear. We're just going to have cos theta. In the middle, we're going to get theta over sine theta. And on the right, we're going to get 1 over cos theta. Now, like I said, we're trying to get that target function of sine theta over theta. So now we're going to take the reciprocal. Take reciprocal. When you take the reciprocal of an inequality, it ends up flipping the inequality. So this becomes 1 over cos theta greater than or equal to sine theta over theta greater than or equal to cos theta. But for doing the squeeze theorem, it's not nice to have the biggest one over here and the smallest one over here, so I'm just going to reorder it. Reorder. So if the smallest one is cos theta, I'm going to put that on the far left. The next one is sine theta over theta. And then the next one is 1 over cos theta. All right, well, let's look at what we have. So we're trying to go to 0. So the limit as theta approaches 0 of cos theta, well, that's just equal to cos of 0, which is 1. The limit as theta approaches 0 of 1 over cos theta, well, that'll be 1 over cos of 0, which is also 1. So, therefore, by the squeeze theorem, the limit as theta approaches 0 of sine theta over theta must also be equal to 1. Because, well, the squeeze theorem. If the left-hand side is 1 and the right-hand side is 1, and this number must be squeezed between 1, well, the only number between 1 and 1 is 1. So there's the end of our proof. And we can put a little box that indicates we're done. Again, sometimes mathematicians will write QED instead of a box. And either way, they just mean that the proof has been completed, that it's been put to rest, that we've demonstrated that this is indeed true. So here's our proof, and one of the first proofs we've had in the course. It's a very nice proof, a little complicated with the diagram, but in the end, quite an elegant use of the squeeze theorem to show that this limit is equal to 1. Now, another theorem that's also useful in calculus that we're going to need to take a look at is the limit as theta approaches 0 of cos theta minus 1 over theta. Now apparently this one is equal to 0, and we could try plugging it in, but if you plug in theta equals 0, cos of theta is 1. So 1 minus 1 is 0, 0 over 0. Yeah, we're going to need to do some more work. And this theorem is actually easier to prove than the previous one. It's not quite as long because we have some information available to us. So what I'm going to do is I'm going to start with the limit we have. Limit theta approaches 0 of cos of theta minus 1 over theta. And I'm going to do the rationalizing trick. I'm going to multiply by cos theta plus 1. Cos theta plus 1. Well, that's going to give me the limit theta approaches 0 of cos squared theta minus 1 over theta. And then again, I don't expand out the bottom, cos theta plus 1. Now thinking about your trig identities lists, is there an identity I could use here? Cos squared theta minus 1. Is there an identity that might be handy? Well, if I have sine squared theta plus cos squared theta equal to 1, if instead I had cos squared theta minus 1, well, I could move the sine squared to the other side and make it negative sine squared theta. So this is theta approaches 0, negative sine squared theta over theta cos theta plus 1. Now, remember, we just finished proving that the limit as theta approaches 0 of sine theta over theta is equal to 1. And we're allowed to use that in our next proof, because you're always allowed to use the previous things you've proved. You can always use what you've proved because now it is true and you can use it in your next argument. So what I'm going to do is I'm going to write sine squared theta as the sine theta times the sine theta, because that's what sine squared means. It means that you have literally two copies of sine. So I've got a negative in front, I've got a sine theta, then I've got another sine theta. I'll put the first one over theta and the other one over cos theta plus 1. As long as this is still multiplication, I haven't done anything, I've just rearranged the expression. Now here we have sine theta over theta, and we can use the fact that that limit must be equal to 1. So this is going to be equal to negative 1 times, here, sine theta over cos theta plus 1, well, that's going to be just plugged in. Sine of 0 is 0 over 1 plus 1. So we've got negative 1 times 0, which is just equal to 0. And there you go. There's our proof. We have the nice finished proof of the statement. And again, the interesting thing about this statement and this theorem is that we were using the previous theorem. This is quite a common technique in math. Once you've finished proving one thing, you can use it to prove the next thing. Now, these I like to think of as special limits. So the limit theta approaches 0 of sine theta over theta equals 1. I think about this like a special limit. And special in the sense of if you ever come into contact with sine theta over theta as theta approaches 0, you can always just write that as 1. This is a limit you now know. It's a limit you could memorize. You don't have to try to figure this one out because we've proved that it's equal to 1, so you can use it as a special limit at any time. Now, if you're struggling with any of these proofs, I recommend you check out some of the other videos on my YouTube channel. I actually have full proofs of all of the theorems you're going to need for the test and the exam on a playlist on my channel. So go ahead and watch those proofs if you want to see these done a second time. So that's the end of the trig limits section. Hopefully you enjoyed this video, and as always, thanks for watching.